Now we're going to talk about imaginary numbers and how to simplify them. So let's get started with, in my opinion, where this all kind of came from. So we know that 1 squared is 1. And we know that -1 squared is -1 times -1, which is +1 as well, right? We also know that the square root of 1 is 1 because when the square root's already on the problem, in other words, you did not square root both sides, but they ask you what the square root of a number is. It's supposedly understood, which means somewhere in the past you were supposed to have been told this, but I'm not actually sure where that occurs. It's understood that it's asking you for the primary or the principal square root, which is the positive one. So the square root of 1 is a positive 1. This particular version, though, where you square root both sides, when you square root both sides and say, what did you square to get 1? You put a plus or minus here, and the square root of 1 is 1, and you get both potential answers. You could have squared a -1, and you could have squared a 1. Now, so back to where this, I think, came from. So what if I had the square root of -1? And the square root of -1 is, what do you multiply by itself and get a -1? Well, as we just looked over here, 1 squared is 1 times 1, which is a positive 1. And -1 squared is -1 times -1, which is a positive 1. So there's no real number that you can multiply by itself. By itself is the key, and get a -1. So they defined this. And when they defined something, that means that it they don't have a proof as to why it works. It just makes it work, and it works in real life from observation. And so they just defined that, and we just get to live with that, but there's no proof of it, okay, in this context, right? Now, so the square root of a -1 is defined as I, sort of like pi, the symbol pi is 3.14 and a bunch of other decimal places, right? Sometimes symbols represent numbers. So I represents the square root of a -1, right? Now, once we have that concept, it kind of goes like this. All right, so if you have the square root of 49, well, what multiplies by itself and gets you 49? 7 is one possibility. It's the primary one. It's the positive one, right? What about the square root of -49? What do you multiply by itself to get -49? Nothing. But we can think of this as 49 times a -1. And the square root of 49, we know, is 7. And the square root of -1, by definition, is an I. So the square root of -49 is 7i. So the square root of -100 can be treated as the square root of 100 times a -1, which is the square root of 100, which is 10. And the square root of -1 is defined as I. Now, after people do a few of these, they sort of start shortcutting it, and it goes like this. If you see this this negative right there, they go, oh, this is going to be an imaginary number if it's a square root. So I'm just going to pull this out as an I, and then the square root of 100 is 10. So they just sort of do it that way after they get used to it. But slow and correct is better than fast and wrong. So if you are still just sort of hanging on to this concept, put all these steps in. Now, there's a couple of things you have to watch out for if you have negatives underneath here. You know that if you have the square root of 4 times the square root of 9, this is the square root of 36. You can multiply the insides together, and this would be 6. If, however, you have negatives underneath there. That takes precedence. So you have to clean up that negative, that imaginary number, before you start thinking about the 36. So it is not correct to say this is the square root of a positive 36 because a negative times a negative is positive. That's not right. You can't do that. Okay. So what you have to do is to say, all right, the square root of a negative 4. The negative is an I, and the square root of 4 is 2. The square root of negative 9, the square root of an understood negative 1 is I, and the square root of 9 is 3. So 2I times 3I is 6I squared. You okay? All right. So it turns out to be I squared. Now, remember that I represents a number that we can't simplify, right? I is the square root of a negative 1, which is, a number, all right? So if I square this, all right, this square cancels that square root. So I squared is actually a negative 1. So I can clean this up. So this is 6 times a negative 1, which is negative 6. See the difference? All right, so let's try another. If you have negative 5, square root of negative 5 times the square root of negative 15, you cannot multiply the insides together right now and say it's a positive something. You have to sit there and say, no, all right, it's negative under a square root, so that's an imaginary component. I have to clean that up first, have to simplify that first. So I would have the square root of 5 and an I times the square root of 15 and an I. So even if you cannot simplify the actual number, you can still pull the I out to simplify the negative, the square root of a negative. So you have I squared, and the square root of 5 times the square root of 15 is 75, which is 25 times 3. So you have I squared, the square root of 25 is 5, and the square root of 3 cannot be simplified. So you have 5 I squared square root of 3. There's sort of an understood order of kind of what they're expecting first, second, and third. And to me, it's sort of like the further it diverges from just like a constant, like this is a 5. Okay, I squared is a little cleaner looking than a square root, right? So it's sort of like the more the appearance deviates from that of just a simple number, then it goes farther toward the end. Okay, I don't know if that helps you or not. Normally the radical is at the end. I think the reason that the radical is at the end is because, some of us are not the best writers. I'm certainly not. So if you have it looking like this and the I squared follows behind and you are a little bit messy, the question becomes, is the I squared under the radical or is it after the radical? So if the radical is the last thing in your answer, then that's the last thing. You don't have to worry about whether this is under the radical or not if you're a little bit messy, right? Now, I squared is a negative 1. So a negative 1 times 5 is a negative 5 square root of 3. Doing okay? All right. Now, what can you do with these imaginary numbers? Pretty much anything that you've done with any other kind of real number. Now, they do talk about what's called a complex number. And a complex number is of the form a plus bi, something like 2 plus 3i. That would be like an example of a complex number, to where this would be your real number. It goes first, and this is your imaginary number, and it goes last, kind of like standard form. Okay? So you can make any number look like a complex number. If you have just a real 5, that's all you had, and somebody said express it as a complex number, you can say I had 5 real and no imaginary. You could force it to look like a complex number. Likewise, if you have 3i and they want it in complex form, you can say I have 3 imaginaries and no reals. Right? Now, what can we do with these things? We can add them, subtract them, multiply them, divide them, do all sorts of neat things. So if you have 3 plus 4i plus minus 2 plus 6i, and I've just grouped these together so you can get used to this complex number format, you add like terms to like terms, so you add your reals together and you add your imaginaries together. So you would add this 3 and this negative 2 together and get 1. And you would add this 4i and this 6i together and you would get 10i. Right? Likewise, if you have 6 minus 5i and subtract a 1 minus 7i, this subtraction right there is going to distribute. So you'd have 6 minus 5i minus 1 plus 7i, because this is going to distribute just like it always has. And then you combine your 6 and your negative 1 and your minus 5i and your 7i, and you would get 5 plus 2i. You hanging in there? All right. You can multiply. It's sort of like if you took 8 times 8 plus x, right? You could distribute this 8 over. So in a way, the imaginary, the little I, acts kind of like a variable, but it is a number, right? So 8 times a negative 8 is negative 64, and 8 times a negative I is negative 8i. And they are not like terms, so you cannot add them up together. All right. Let's do 2i times 3 minus 7i. So you would have 2i times 3 is 6i. 2i times minus 7i is minus 14i squared. So you have 6i minus 14. And remember that this I squared is actually a negative 1. So you have 6i, and negative 14 times negative 1 is plus 14. Now, that's an accurate answer, but it is not considered standard form. Standard form is a plus bi, where you have the real number in front. So this would be 14 plus 6i. All right. Let's keep going. So what if you have 3 minus 4i times 7 plus 2i? So this is either, you might multiply this out using the distributive property or the FOIL method. And so you would say 3 times 7 is 21. Then 3 times 2i is 6i. Minus 4i times 7 is minus 28i. And you'd have minus 8i squared. So 21. 6i's minus 28i's is minus 22i's. You count them like you do x's. And you have minus 8 times, and I squared is a negative 1. So you have 21 plus 8, right? 21 minus 22i plus 8. So this is 29 minus 22i. So in some ways it acts like a number, and in some ways it acts like a variable. Now watch what happens when you multiply conjugates. And remember that conjugates are the same two binomial entities, but the sign in the middle is different. One's a plus and one's a minus. So we have both of them have a 5, both have a 6i, one's plus, one's minus. These are called conjugates of each other. And when you multiply these out, you get the difference of 2 squares, right? And you can use that formula of multiplying conjugates to get the difference of 2 squares to go straight to the answer. But, let's work this out the long way. So 5 times 5 is 25 minus 30i plus 30i minus 36i squared. So see, these two terms cancel each other out, and you have 25 minus 36 times a negative 1. So 25 plus 36 is 61. Now, this is kind of an interesting concept, and they use this quite a bit. So this is a technique you need to know. When you multiply conjugates together, your imaginary terms fall out, and you're left with pure real. And that's kind of cool. All right. I don't know if the hair on your arms is sticking up or not, but it's actually kind of cool. So if you have imaginary numbers or a complex number, and you're trying to kind of like when you used to rationalize denominators, with square roots, trying to get rid of the square root and get a nice round rational integer. If you're trying to get a real number from a complex number, multiply it by its conjugate. All right. Now, if you have negative 4 plus 2i squared, remember this is a binomial square, so you cannot just square what's in there. You'll miss that middle term. So you would say negative 4 times negative 4 is 16. Negative 4 times plus 2i is negative 8i. Then you'd have another negative 8i, and then you would have plus 4i squared. So it's 16 minus 16i plus 4 times a negative 1. So 16 minus 16i minus 4 is 12 minus 16i. All right. Negative 4 plus 2i squared is not negative 4 squared plus 2i squared. You cannot just square what's in there, right? Because it's a binomial. So don't do that. All right. Now, so there's just a few more things we can think about. If you have something like negative 70, square root of negative 70 over the square root of negative 7, then you can think of this as, well, there's an I and a square root of 70 because there was a square root of a negative, and an I square root of 7, and these two i's cancel, and the square root of 70 over the square root of 7 is the square root of 7 times the square root of 10 over the square root of 7, which is the square root of 10. Now, you could also think of it as this way. Goodness. Let's try that again. Square root of negative 70 over the square root of negative 7. You remember that you can pull them apart, kind of going this way, and you can put them together going this way when you were doing square roots before. So a negative over a negative is a positive, and 70 over 7 is 10, so you'd have the square root of 10. Now that's kind of, I don't know about you, but it's kind of creepy because I should say things like that. All right, we had a problem that looked kind of like this, and not like that. Mine 4 looks like a 9. And we said we cannot say this is a positive 36. We had to say the square root of a negative 4 times the square root of negative 9 is 2i times 3i. So it was 6i squared, which was a negative 6. All right. So multiplying them like that, we can't just multiply the insides, but dividing them, we can divide the insides. And that's just something you have to sort of adapt to. I hate to say it. All right, what if you have a problem like this? And you can say, well, I'd have negative 5 plus the square root of 25 times a negative 2 over 10. So negative 5 plus the square root of 25 is 5. The square root of this negative is going to be I, and the 2 is still inside the square root because you can't simplify it anymore. And you can see that there's a 5 in common, right? There's a 5 in common here and in here. It may help you to write it this way. Negative 5 over 10 plus 5i square root of 2 over 10. So this reduces to negative 1/2. And then this 5 over 10 reduces to I square root of 2 over 2. All right, now let's talk about this. Different computer graded systems, different teachers, different books, have different things about what they do and do not want to see. Okay, I would be okay with this this answer. I would be okay with negative 1 plus I square root of 2 over 2. That would be good with me. May not be good with your teacher. If your teacher says, I want A plus BI form, all right, then it would be incorrect to leave it as negative 1 plus I square root of 2 over 2, because do you see how it's not really two separate terms? It's a single fraction. So A plus BI form says, I want you to split it up like this, right? Something plus or minus something else. And if it truly wants that form, most likely the I is out here, so that A is negative 1/2 and B is the square root of 2 over 2. So this I is just hanging around right there. Now, only you know what your teacher wants and what you've been presented and how they demonstrate it. So be sure that you replicate whatever it is that they showed you. Now, what happens if we have something like 14 plus 5i over 3 plus 2i? Now, just like in the past, if you had something 1 over 2 plus the square root of 3, they did not want square roots in the bottom of a fraction, so they would ask you to rationalize it, and what you would do is to multiply it by its conjugate, because then the square roots would cancel each other out, right? And you would have a nice round rational number in the bottom. That's why they called it rationalizing the denominator. And then you would have an irrational number in the top, but that's okay. They just didn't want them in the denominator. Then when you get to calculus class, they go, we don't care. Leave it down there. All right, we're just fine. But up until calculus, they don't like that. All right. Now, it's sort of the same principle here. We don't mind imaginary numbers in the top of a fraction, but it's considered bad form or not completed, not simplified, if you have imaginary numbers in the denominator. Okay, and it's just tradition. Okay, it's just tradition, because like I said, when you get to calculus, they go, we know you know how to do that. Let's leave it alone. It's fine. All right, mostly. All right. Now, so we're going to use that same principle we had from our past experiences with square roots, and we're going to multiply this by the conjugate, and we have to multiply the top by the same thing to be legal, so we're multiplying by a version of 1. 3 minus 2i over 3 minus 2i is 1 itself, right? So I'm multiplying by 1. So that, in effect, does not change the value. It changes its appearance, but it does not change the value of what it is that we are computing. Okay? Now, so when we do that, we're going to do the distributive property or the FOIL method, whichever one you use, and let's do the numerator. And so 14 times 3 is 42. Then you would have minus 28i, 14 times minus 2i. And then 5i times 3 is 15i. And 5i times negative 2i is negative 10i squared over 3 times 3 is 9. 3 times minus 2i is minus 6i. 2i times 3 is a positive 6i. And 2i times negative 2i is negative 4i squared. Now, y'all, you absolutely cannot sit here and say things like, these I squares are going to cancel, or 4 goes into 10 so many times. Those are not factors of each other. You've got all these pluses and minuses here, so you cannot reduce it unless you have factors. You don't have that. So we have to clean this up. So you would say, all right, I have 42 Okay, minus 28i plus 15i is minus 13i, and minus 10 times a negative 1 over 9. Minus 6i plus 6i cancels. Minus 4 times a negative 1. So you have minus 10 times negative 1 is plus 10. So 42 plus 10 is 52. Minus 13i over 9 plus 4, right? 9. Negative 4 times negative 1 is plus 4. So this is 13. And you look at it and go, I wonder if 13 goes into everything on top. So this is 52 over 13 minus 13i over 13. And 13 goes into 52 4 times. And the 13's cancel. Then if you have something like a monomial, you still multiply it by its conjugate. And negative I is 0 minus I, so its conjugate is 0 plus I. So this would be 12i over negative I squared. So this is 12i over negative 1, which is 12i, over a plus 1, which is 12i. If you had 5 over 9i, this is considered to be 0 plus 9i, so its conjugate would be 0 minus 9i, so you'd multiply by negative 9i, and the top by the same thing to be legal. So you'd have negative 45i over negative 81i squared. So you have negative 45i over negative 81 times negative 1. So it's negative 45i over positive 81. And there's a 9 in common, so you can say it's negative 5i over 9, which would probably work for me. But in the a plus bi form, it's negative 5/9 I. So this is 0 minus 5/9 I. This is a and this is b, and there's your I for a plus bi form. All right. So there's only one more thing to think about, and let's talk about, is the only power you're going to see on an I a square? Is that as high as it's going to go? And the answer to that is no. All right. So here's how this works. And books show you all sorts of complicated ways to solve this. And I'm going to try to show you a fast way. All right. So we know that I is defined to be the square root of negative 1. And we know that I squared is the square root of negative 1 squared, which would be negative 1. We know that so far. I cubed would be I squared times I. I squared is negative 1 times I is negative I. And I to the fourth is I squared times I squared, which is negative 1 times negative 1, which is positive 1. Okay, so what I've got is I equals itself. Okay, I squared is equal to negative 1. I cubed is negative I, and I to the fourth is positive 1. All right, now I to the fifth is I to the fourth times I. I to the fourth is positive 1 times I is I. I to the sixth, just hang in there with me a minute. I to the fourth times I squared is 1 times negative 1, it's negative 1. I to the seventh is I to the fourth times I cubed. So it's 1. I cubed is negative I. I to the eighth is I to the fourth times I to the fourth, which is 1 times 1, which is 1. Okay, now look right here. And look right here. All right, so let's look right here. And I'm going to say it to you this way. The pattern is I, 1, I, 1, and the 2 in the middle are negative. All right, other than saying I, negative 1, negative I, 1. Okay, which is just a mouthful. Okay, I, negative 1, negative I, 1, I say as I, 1, and the 2 in the middle are negative. The first time I did that to a class, I hadn't been teaching very long, and I said, so see, it's I, 1, and the 2 in the middle are negative, and they started telling me this, kind of like I was saying, I won, I won, right? And so they were going like that out in class, going, I won, and the 2 in the middle are negative. And I said, whatever makes you smile in a math class, I am totally in. All right. So the pattern is I won, and the 2 in the middle are negative. And that happens down here again. I won, and the 2 in the middle are negative. So the pattern just goes on and on and on and on and on. Okay, it never stops. And so we don't care how many times I go through the pattern. I just want to know where I stop. Okay, so for instance, let's look right here. If I had I to the seventh, we just figured out over there what it is, but let's do it this way. So in the pattern, there's a pattern of 4, right? There's 4 entities in this pattern. So we are literally going, the pattern of 4 goes into 7 one time with 3 left over, a remainder of 3. So what it's going to do is it's going to pass through this pattern one time, and then it's going to kick back up here and go down to 3 and stop. So I to the seventh should stop at the same spot I cubed is, which is negative I. And is that what we got last time? Yes, it is. So teachers generally ask you some of these questions because they actually try to get you to do something like saying I to the seventh is I to the fourth times I squared times I, and I'm like, oh my gosh, I'm not even sure now what I'm doing. So I'm just telling you that all you have to do is count how many times you go through the pattern and where you're going to stop. So if you have something like I to the 29th, okay, let's take this out. Okay, so 4 goes into 29. How many times? 7 with a remainder of 1. Right? So what's going to happen is it going to go 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times through the pattern, and then kick back up here and stop at I to the first. So I to the first is I. And you're done. Okay? How about I to the 40th? All right? 4 goes into 40 10 times with no remainder. Okay, now wait a minute. Where does 0 go? I don't see a 0 over there. I have 1, 2, 3, 4, but I don't have 0. Okay, we'll look right here. This 4 that's down there, right here. 4 goes into that 4 one time with nothing left over. So if you have 0 left over, the leftover kicks you back up to the top of the list. So if you have nothing left over, you're at the bottom of the list. So this is 1. Right? So if you have something like I to the 21st, no, 22nd, right? Here's what you have to remember. You go, the pattern is I, 1, and the 2 in the middle are negative, right? And that came from, and this is how I do it. I put all my I's down, and then I count 1, 2, 3, 4. All right. So you build your pattern by going over here and going I1, and the two in the middle are negative. And then over here on this side, you just count 1, 2, 3, 4 with your eyes. So here we go. I to the 22nd. 4 goes into 22 5 times with 2 left over. So here's the 2 left over. Just -1. All right. What if you have I to the -16? Well, negative powers mean you move it to the other side of the fraction bar. So you have 1 over I to the 16th. Okay, let's see. 4 goes into 16 4 times with nothing left over. So down here is the 0 remainder. So this is 1 over 1, which is 1. And if you had I to the -30th, it's 1 over I to the 30th. All right? So it's 1 over. Now, let's talk about 30. 4 goes into 30 7 times with 2 left over. So this is your 2 left over right up here. Right up here is your 2 left over. So it is 1 over a -1. So this is -1. So I hope that helps with your imaginary mechanics of how to add, subtract, multiply, simplify, divide them as if they're a fraction, and how to simplify higher powers of I. And I hope that helps. See you in the next video.